Something happened where I wasn't recording, so what I've done so far we missed, and I'll start real quick again because I think I lost it. I'll recopy it. Let's continue on. All right, let's look at number 6. If a balloon has a pressure of 650 torr and a volume of 1.9894 liters, what is the pressure of the balloon if the volume is increased to 5.133 liters? What are we trying to find? A final pressure, which I'll call P2. What are we given? The initial pressure. How many torrs? 658. The initial volume, 1.894 liters. What are we given? A final volume. How do you know that? The volume is increased to something, in this case 5.133. Notice right here, you only have pressure and volume. Temperature is not included, weight is not included, so use Boyle's law, P1 times V1 equals P2 times V2. If you look at important information, this is given to you. It's also given P1 initial pressure, V1 initial volume, P2 initial final pressure, V2 final volume. What are we trying to find? P2. So we need it alone on one side. Remember, anything divided by itself is number 1. So if I want to get rid of V2 and I'm multiplying it times P2, I can divide by V2. Whatever you do to one side, you have to do to the other. Anything divided by itself is 1. 1 times P2 is P2. It's equal to this. Dr. White likes to rewrite it. He's done the hard part figuring out what these are. I now put those in. 3 significant, 4, 3, actually 4. And when you do a multiplication division, the number of significant figures in your final answer is the same number of significant figures of the number you're multiplying or dividing that has the lowest significant figures, so this should be 3 significant figures. And if we look at number 7, the piston has a volume of 22.4 liters at 12.34 atmospheres. That's pressure. You should know atmospheres, millimeters, mercury, and torr are pressure measurements, just like L, liter, is volume. What is the volume of the piston when the pressure is reduced to 3.567 atmospheres? And here we're trying to find the final volume, V2. We're given initial volume and pressure right here, and we're shown when the pressure is reduced to something, in other words, changed, that's the final pressure volume, in this case, pressure. Notice here, only volume and pressure are involved. As soon as you see that, Boyle's law, P1 times V1 equals P2 times V2. What are we trying to solve for? V2. We want it alone on this side. How do we get rid of P2? Divide by P2. Anything divided by itself is the number 1. 1 times V2 is V2. But whatever you do to one side, you have to do to the other. And I did. And hopefully you did too. And now we have this. I'm going to rewrite it. P2 equals P1 times V1 over P2. Put the numbers in. I didn't do it the last problem, but notice atmospheres divided by atmospheres cancel out. I'm left with liters. Yay, that's what I want. And 4, 3, 4 should be 3 significant figures. Let's do number 2 first, number 10 first. All right. What I don't have here, but would be in this corner, 15 points. Everybody see that? Everybody see problem 10, 15 points? Hopefully it came out. All right, let's get back to the actual problem. And the question is, if you burp 86.75 grams, that's going to be a heck of a burp, of carbon dioxide at 545 millimeters of mercury, 34.6 degrees C, what's the volume of your burp? So what are we being asked to find? The volume of your burp. What are we given? The weight of the carbon dioxide you burp, the pressure you're burping it at, and the temperature you're burping it at. Now, notice nothing is changing. Also 15 points, and that means PV equal nRT, the ideal gas law. What are we trying to solve for? P. Therefore, on this side, how do we get a V, I should say? How do we get rid of P? Divide by it. Whatever you do to one side, you have to do to the other. So I did. Now I'll rewrite it. P divided by P is 1 times V is 1 times V is V, and that equals nRT. Now, something, hold on one second. Everybody see the ideal gas law in your, this is from important information, test number 3. If you look at the top of the page, that's the file name. And this is going to be given to you. Now, remember, PV equal nRT. P is the pressure. It has to be in atmospheres. Common mistake, you're never going to be given an atmosphere, because I've never seen a gauge in my life that measures pressure in atmospheres. It's always in torr, millimeters of mercury, or in the United States sometimes inches of mercury, which I won't use in this class. And therefore you have to convert pressure to atmospheres. That's a common mistake. I will always give volume in liters, or you'll have to calculate it. Now, N is N is moles, but you're going to be given grams. So you're going to have to go convert grams to moles. Temperature is in Kelvin, and you're only going to have to convert degrees C, because I've never seen a thermometer in Kelvin, to Kelvin. And if we scroll up or down somewhere, there it is, hidden away right here. I give you Kelvin equals degrees C plus 273. And as I mentioned, I also give you this. I would highly recommend this weekend you look at this. But come back here. When you're doing the ideal gas law, if you're using pressure in your calculation, you have to convert it to atmospheres. Liters, you'll always be given volume in liters. You're going to be given grams, which you're going to have to convert to moles. And Kelvin temperature here, you're going to have to convert that from Celsius or centigrade to Kelvin. R, which is the universal gas law constant, I will give you, as you see here. And I also give you the units. And this tells you this is pressure, you got to do moles, and this is your temperature. And that also reminds you got to do conversions. Boy, I'm being too nice to you people. So at this point, we know V equals nRT divided by P. And now what we have to do is, first of all, pressure is in atmospheres. So I'm going to go from millimeters of mercury to atmospheres. We just did this. Atmospheres go on top. Millimeters of mercury or torr would go underneath. Where do you get this? 1 atmosphere, 760. Remember, these are exact numbers, 3 significant, 3. Now, this is one of those problems where you're doing multiple steps, and what I do is I calculate both, rounding off at each step, like you'll see on my answer, or rounding off at the end, and I calculate both. Now, temperature you're given in degrees C, and notice I have 0.6. This was a trick. I don't think I'll do it on the test, but just in case, remember when you're doing addition, you get the same number of significant figures past the decimal point as the number with the fewest. 273 is the exact number, 1 past the decimal. That's why you keep the 0.6. Even though this is 4 significant figures, it's 1 past the decimal. Finally, N is moles. And we want moles of CO2, but we're given grams. How do we go from grams to moles? Use your good buddy, your good friend, unit analysis. Moles go on top, grams go underneath. Where do you get this ratio? If you notice important information, test number 3. Everybody see the important information on there? Thank you. 1 mole of a compound equals the molecular weight in grams, and the molecular weight of a compound is the sum of all atomic weights. Therefore, if I go back to my problem, where do I get 1 mole relationship of CO2 to grams of CO2? 1 mole is the molecular weight. Over here, the molecular weight is 1 carbon, 2 oxygens. Each carbon to 3 significant figures. You will be given the same green periodic table, is 12.0. 1 times 12.0 is 12.0. 2 times 16.0 is 32.0. Add them up, 44.0. 4 significant, exact number, 3. My answer here is 3 significant. So now I can put in here N, 1.97 moles. R, it's given right over here. It's also important, 0.0821 atmospheres, liters, mole K. The K, Kelvin, which we calculated here, 307.6. P, pressure in atmospheres, this, oops, and the answer is 69.4 liters, which is not realistic. I don't think our lungs have that capacity. Remember a 2-liter bottle? You've done 35 of those or approximately, no. But at least you get a feel how to do ideal gas law. And thank you everybody for the cute emojis. All right, let's do one more. Now, if we look at number 9, we have what is the weight of 5.77 liters of oxygen gas, O2, at 101 C and 678 torr. What are we trying to find? Weight, which in this class is always going to be grams, O2. We're given a volume, given a temperature, given a pressure, and important information, you're given R. Now notice here, we need a weight. PV equal nRT, none of these are a weight. However, N, moles, I can convert to weight. You did that in test 2. So for this type of problem with PV equal nRT, you need 2 steps. First step, calculate or determine N, moles. Second step, go from moles to grams. So how do I solve for N? I get rid of RT. Why am I using PV equal nRT? I have a gas. I see I'm trying to get a weight. I'm giving volume, temperature, pressure. Nothing changes. That immediately tells me PV equal nRT. So to get rid of RT, I divide by RT. Whatever I do on this side, I do on this side. I now have N equals PV over RT. I rewrite it. And now remember, pressure has to be in atmospheres. So here I convert it. Have torr going to atmospheres. Atmospheres goes on top. Torr goes underneath. Remember, 1 atmosphere is 760 torr. These are exact numbers, 3, 3. Next, volume is already in liters, so I don't have to do anything different. And I'll always give that to you that way. That's my special little gift to you. And here we next have R. Well, that's given to you. And finally, T. T is temperature, but it has to be in Kelvin. And Kelvin equals degrees C plus 273. Degrees C was 101. Add 273 and you get 374. Now I put those numbers in, 3, 3, 3, 3 significant figures. My answer for step 1 is 0.170 moles of O2. But I want grams of oxygen. So second step, moles to grams. I have these many moles. I want to get the grams. Use your good buddy, your good friend, unit analysis. I have to get that in. And what we're trying to get to goes on top, grams of O2. What we're trying to get rid of, moles of O2, go underneath. Where do I get this numbers for that ratio? 1 mole of a compound equals its molecular weight. Over here, 2 oxygen, 2 times 16.0. The 3 significant figures, the molecular weight of oxygen, atomic weight of oxygen is 16.0. That's 32.0, go here and here. Exact number, 3, 3. And if you round off the very end or in between like I do at each step, you get the same answer both ways. That amount of oxygen is 5.44 grams. I'll let you look at 11 on your own. We already did something like that. Uh-oh, guess what Dr. White forgot in the problem set? Oh no, I forgot something. Guess what? Through the miracle of modern chemistry, in other words, I know it, I'm going to give you a couple problems to do on your own that I forgot. All right, everybody see, oh, I want red. Everybody see 5 points on there now? Thank you, Kim. Everybody else too. In there. All right, I'll do this one, and then you can make up your own and try them. I'll do one for you too. In a mixture of nitrogen gas, N2, and ammonia, you have a, let me move me out of the way so you can see it. You have a nitrogen partial pressure of 401 torr, an ammonia partial pressure of 202 torr. What is the pressure of this mixture? Well, what are you trying to find? P total. What are you given? Partial pressure nitrogen equals 401 torr. Partial pressure of ammonia, which is a gas at room temperature, is 202 torr. So what do? Dalton's law of partial pressures. P total equals the sum of all the partial pressures in that mixture. So therefore, P total for this problem equals the partial pressure of nitrogen plus the partial pressure of ammonia. In this case, it's 401 torr plus 202 torr. Hang on while I get my calculator. No, I can do this in my head. And that's 603 torr. And that's how you do it. Remember, when you're given partial pressures or asked to find a total or partial pressures, you need Dalton's law of partial pressures. P total of this mixture is equal to the sum of the partial pressures. Remember, partial pressure is the pressure of that gas in that mixture if it was alone. We were in COD. I had to be quiet while I was writing this on the board too. Also, once in a while, I would mess up writing on the whiteboard in a classroom. All right, here's one for you to have fun. A mixture of nitrogen, oxygen, and argon has a nitrogen partial pressure of 301 torr, a oxygen partial pressure of 101 torr, and an argon partial pressure of 202 torr. What is the total pressure of this mixture? Your turn. Have fun. And when you're done, don't forget, give me a thumbs up or a smile or give me the high sign. I've said, don't forget, when you're done, give me a thumbs up. All right, anybody need more time? Going once? Going twice? Let's do this. What are we being asked to find? The total pressure, P total. What are we given? P nitrogen, the partial pressure nitrogen, is 301 torr. Partial pressure of oxygen is 101 torr. And partial pressure argon is 202 torr. And if you notice, whenever you see partial pressure and total pressure, Dalton's law of partial pressures, P total equals the sum of all partial pressures and in this case, P total equals the sum of partial pressure nitrogen plus partial pressure oxygen plus partial pressure argon, and that's 301 torr plus 202 torr plus 101 torr. If I did my math right, that's 1 plus 2 plus 1, 604 torr. Since I did it in my head, I could be wrong. So everybody, give me a thumbs up if Dr. White did it correctly. Okay, look out, I'm on a winning streak. And that's the problem set for gases. If hopefully you tried this on your own. Remember a long time ago when we started this semester, I talked about riding a bicycle in the Blu-ray and watched how to ride a bicycle over and over again. But when you get on the bicycle, first time you'll fall off till you practice. Watching me do the problems, it's like watching the Blu-ray. It looks easy until you try it yourself. I'd highly recommend you try it yourself. Any questions on gases? I gotta find a way to reduce my ear. That's always one of the amazing things of life, and that your ears keep growing. Now, if I could only move my hair to do the same thing more. All right, let's go back to solutions. All right, hold on one second. All right. That's why I can't find it. All right. On Monday, I was talking about molarity, which is concentration, how much of a solute is present in a solution. And the important thing I taught you was molarity, capital M, is moles per 1 liter of solute. And hold on, let me get rid of all those squiggly lines. And remember, 1 liter equals 1,000 milliliters. Therefore, the one you'll use is molarity equals moles solute per 1,000 milliliters of solution. This is an exact number. This is calculated, so that's molarity. And one of the things I taught you was what does this mean? As soon as you see the capital M, you know that's molarity. And what that really means is 1.75 moles NaCl per 1,000 milliliters. And that tells you. I'm going to let you try one. What does this mean? Well, what does that mean? Your turn. All right, I'll give you 8.9 seconds more. 1, 2, 3, 4, 5, 7. My timer doesn't work that well. 8, 8.2, 8.5, 8.6. Time's up. Let's take a look. What does this mean? As soon as you see capital M, that's molarity. Remember, molarity is capital M. And it's moles of solute per 1,000 milliliters. So what does this mean? 0.024 moles KOH, potassium hydroxide, per 1,000 milliliters. And that's what that means. Now, on Monday, we did the following. Let's do another one. I'll do this for you because we've already done one, but this is a refresher. The question is, how many moles of sugar are in 451 milliliters of a 1.02 molar sugar solution? So what are we trying to find? Moles of sugar. Says it right here. What are we given? How many milliliters of solution we have? And we're also given this. As soon as I see capital M, what does that mean? 1.02 moles of sugar per 1,000 milliliters. And now the only number I really have to work with is this. I want to get to this moles of sugar. And now I'll use my good buddy, my good friend, unit analysis. Whatever I'm trying to get to goes on top of the ratio. Whatever I'm trying to get rid of goes underneath. And therefore milliliters go here, moles sugar goes here. Where do I get these numbers? From right here, because I knew this really meant this. So I have 1.02 moles of sugar per 1,000 milliliters. Notice milliliters divide out. I'm left with the right units. Remember, 1,000 is an exact number. It has no input into how many significant figures your final answer has. Here I have 3 significant figures. Here I have 3 significant figures. Therefore, my answer should have 3 significant figures. Hang in there while I open my spreadsheet. And here's the number you get if you do the calculation. That's 451 times 102 divided by 1,000. Therefore, 3 significant figures. Keep the 4, keep the 6, keep the 0. Use the 0 to round off. So it'd be 4.06 times 10 to the minus 1. One of your colleagues asked me a question via email yesterday. Do you have to write it in scientific notation? If there are not a lot of zeros, you could also write it like this. Both of these are acceptable, and that's how you do it. And I went a little over. Oh, 1 minute. Let's come back and at 10:55. We got a lot to do, and let's take about a 4-minute break, and I'll see you then. See you in about 4 minutes, 10:55. Time to start again. Let's get going. All right, now, if you saw in the problem I just did, like with sugar, if I needed a certain amount of moles of sugar, all I have to do is measure out a certain amount. If I have a stock solution, like the one I just had was 1.02 molar. Well, the question is, where do you get those? Well, you can buy them, but most of the time in chemistry labs, like at COD, the lab manager makes up what we call stock solutions. Excuse me. And in chemical plants, we make up large stock solutions, and it makes your life easier because you don't have to weigh out something, dilute it, make a solution. You just measure it out. Well, let's look, how do we do that? If you look on your screen, under where I have important molarity questions, we've done 1 and 2, and skip 3 because I'll never put that on test because 3 is part of 4. How many grams of a solute are needed to make X milliliters of a known molar solution, capital M is molarity, of A? So let's look at an example of this. All right, thumbs up, people. Do you see 12 points on the screen? Thank you. All right, let's look at the following. How many grams of NaOH, sodium hydroxide, are needed to make 5.00 times 10 squared, which is 500, but the 3 significant figures of a 3.45 capital M, that's important, NaOH solution. So what are we trying to find? Grams of NaOH. What are we given? How many milliliters of solution we're needing to make? We're also given this. And what does this mean? Capital M tells you molarity, which is moles per 1,000 milliliters. So we're trying to make this, 3.45 moles of NaOH per 1,000 milliliters. Now, let's all right, does everybody see important information on your screen now? Thank you. And if you look right here, I have molarity, moles of solute per 1,000 milliliters. And then right here, oh, look, I have molarity two-step problem. Step 1, milliliters to moles. Step 2, moles to grams. And that's what we need to do. So you need to do 2 steps. And step 1, we're going to go from milliliters to moles. How do we do that? Well, we already did that. We have 5.00 times 10 squared milliliters of solution. We want to get the moles of whatever we're trying to get the grams to. So now I'll say moles of NaOH. And now we'll use our good buddy, our good friend, unit analysis. Whatever we're trying to get to goes on top of that ratio. Whatever we're trying to get rid of goes underneath. And here we have moles NaOH. I have milliliters NaOH. Where do I get the numbers that go in there? Right here. I knew that this meant this, and I know now that 3.45 moles of NaOH per 1,000 milliliters. And notice milliliters divided by milliliters cancel out. I'm left with moles of NaOH, which I want. And now I'll go to my calculator. And we'll do some calculating. And let me test something. Does everybody see the spreadsheet now? You see it? Okay, thank you. All right, let's do it. Now, this is one of those you can round off at each step or wait till the end. And notice I have this, which would be 1.27500 times 10 to the 0. By the way, 10 to the 0 is the number 1. So this is really 1.275. How do I round it off to 3 significant figures? Keep the 1, keep the 7, keep the 2, use 5 to round off. That's 5 or higher. So this becomes 0.3. Forget about the extra zeros. And now it's time to do step number 2 of this.
Dr. White, are you rounding to the 3 significant figures based upon the 3.45 moles of NaOH?
Here's how I do this. Notice 5.00, 3 significant figures. 3.45, 3 significant figures. 1,000 exact number. When you multiply and divide, you get the same number of significant figures in your answer as the number that you're multiplying or dividing that has the fewest. So 3 doesn't, the 1,000 plays no role. Therefore, that's how I got 3 significant figures. Does that help? Whoever asked the question, thank you. All questions in my class are good questions. All right, now, are we done? No, we're trying to get to grams of NaOH. So now we have to do step number 2, which you learned for test number 2. Ooh, we're going to go moles to grams. And now I have 1.73 moles of sodium hydroxide. Hold on, I see someone with a question. By the way, if you wrote down 1.73 times 10 to the minus 2, no, that would be wrong. It would be 1.73 times 10 to the 0, and 10 to the 0 is 1. Let me show you something. Since this is 1 times this is 1.73. Does that answer your question? Something usually on a test I stay away from because I calculate the problems before I finalize the test. When I'm doing this on the fly, well, once in a while this happens. All right. All right, now you know. Let me clean up my screen for a second because I need that room. All right, we're trying to go from moles to grams. I have moles. I want to go to grams of NaOH. How do I proceed? Well, use your good buddy, your good friend, unit analysis. Remember, I'm still trying to get the Guinness Book of World Record for saying it the most in one semester. Somebody keeping count, I hope. Am I up to 1,000,000 yet? I don't think so. But anyways, what do I do? Whatever I'm trying to get to, the units go on top. Whatever I'm trying to get rid of, the units go underneath. Therefore, I have grams NaOH per moles NaOH. 1 mole equals the molecular weight in grams. What's the molecular weight in grams of NaOH? Well, it's the sum of all atomic weights. 1 nitrogen, 1 oxygen, 1 hydrogen, 1 times this, and I'll just put this. This is 23.0 to 3 significant figures. This is 16.0. Dr. White knows this should be hydrogen. And this is 1.01. Add it up. 40.01. Notice this is 1 past the decimal, 1, 2, round this off to 1 past the decimal. So that's 40.0. And now I'll do the math. And notice here, I do get a different answer for each way. And sometimes this happens. And if I look at both of these, this would be 3 significant figures, 6.09 times 10 to the 1, or 69.0, 69.2, or 6.92 times 10 to the first. You can write it either way. I'm going to use scientific notation. And therefore, here, 6.92 times 10 to the first, or 6.90 times 10 to the first. You wanted to write this as 69.2 or 69.0. Either way, that would be correct. And that's how you do it. Now let's go through what I just did. This is important. We're trying to find out how much of a solute, in this case sodium hydroxide, is needed to make this stock solution. How much? 5.00 times 10 squared milliliters. And here's our molarity. We're trying to find grams of NaOH. We're given this. We're given this. Remember, capital M tells you moles per liter, or 1,000 milliliters. You need 2 steps. First one, milliliters to moles. Here's milliliters, here's moles. Use unit analysis to get the ratio. Where do I get these numbers? From right here. And then second step, moles to grams. Where do I do that? Moles to grams, use unit analysis. You get a ratio here, 1 mole per grams of a compound, 1 mole per molecular weight. Calculate the molecular weight of sodium hydroxide, put it there, we're done. Now, before I let you try one, making stock solutions like that is so important that, can everybody see volumetric flaps from Google on your screen now? All right, these are called volumetric flaps. And if we look at one, let's see if I can find a good one. Here, this one. You look right here, it says 10 milliliters, and see the line right there? When you fill this up like a graduated cylinder, you put your solid in there, fill it about this side, put a stopper in, mix it, and then once it's dissolved, you put up enough of the rest of your solvent so the meniscus right to that line. These are very accurate. They're usually accurate to at least 2 significant figures past the decimal. Let's see if I can. Notice this one. It says plus or minus 0.025 milliliters. That's pretty accurate. Now, this is a 10 milliliter, and they come in all sizes. As you can see here, they come in all sizes, usually 500, 1 liter, and 2 liter. I have a collection. I have one like this little one. I have a 5 milliliter. It's so cute. Now you know I'm a chemist. And these are used to make those stock solutions. It's that important that they actually created a special glassware to do that. And why don't you try this one? How many grams of sodium chloride are needed to make 1.00 times 10 to the third milliliters of a 7.65 capital M NaCl solution? Since you may not have a periodic table handy, here are the atomic weights for sodium and chlorine. With that, have fun. Your turn. If you don't have a calculator, just try setting things up. Hint, you need 2 steps. While you're doing that, I'm gonna go check on the election results, if anything's happened. Nope, nothing new from Pennsylvania. Let me check with Nate Silver. He's usually right up to date. Nope. All right, anybody need more time? Let's do this because I got a lot left to do today. We're gonna probably go till midnight. No, I'm just kidding. Oh, come on. Let me ask, thumbs up, people. Do you see the whiteboard and the problem now? Thank you. All right, let's do this. What are we being asked to find? How many grams of sodium chloride? What are we given? A volume. Remember, milliliters is a volume. And we're given this number here. 7.65 capital M sodium chloride. And what does it mean? You should know that's moles of sodium chloride per 1,000 milliliters. And now you need two steps. And as I said, it's an important information. Step one, milliliters to moles. So I have 1.00 times 10 to the third milliliters. I want to get to moles of what? Well, whatever I'm trying to get grams of. So moles sodium chloride, getting ahead of myself. And now use your good buddy, your good friend, unit analysis. Whatever you're trying to get to goes on top of the ratio. Whatever you're trying to get rid of goes underneath. Moles of sodium chloride, milliliters. Where do you get these numbers? Right here. From knowing what this means this. So I have 7.65 moles of sodium chloride per 1,000 milliliters. Remember, this is the exact number. 1,000, 7.65 is 3 significant, and this is 3 significant. So my answer, if you round off at each step, should be 3 significant figures. I'll now go to my calculator. Actually, this one I don't have to. 1,000 divided by 1,000. Oh, I made it easy for Dr. White. is 7.65. And that's 3 significant figures. And now I'll do step number 2. I'll go moles to grams. And here I have 7.65 moles sodium chloride. I want to go to grams of sodium chloride. I use my good buddy, my good friend, unit analysis. Whatever I'm trying to get to, goes on top of the ratio. I'm getting ahead of myself. Slow down, Dr. White. And whatever you're trying to get rid of goes underneath. I can do that. I have grams sodium chloride, moles sodium chloride, and 1 mole equals the molecular weight of a compound. I'll do it over here. Molecular weight sodium chloride. I have 1 sodium, 23.0, 1 chlorine, 35.5, add them up, 58.5, 1 past the decimal, 1 past the decimal, 1, so that's 58.5. Notice moles cancel out. I'm left with grams. And so I'll go to my spreadsheet now. I didn't have to do the last step because I could do that in my head. And I do this, and I'm going to round that off to 3 significant figures. Dr. White's in his 3 significant figure rut again. And if we round that off, keep the 4, keep the 4, keep the 7, use the 5 to round off. That's 4 or higher. So this drop that, increase the 7 to 8 times 10 squared. And therefore, my answer here, since I really didn't have to round off here, well, I did, but it would be the same either way. So let me just check to make sure I calculated, copied it correctly. I did. Actually, I didn't. Should be 4.48. And for those who wanted this one, you could also write 448 grams. So that's how you'd make that kind of molar solution of sodium chloride. All right, let's continue on. Now, everybody, I have here dilutions. When you have to dilute something from a higher concentration to a lower concentration, this is how you do it. Use this formula. But first, click. I decided to make the switch off for this because most of you aren't going to do this, but I just run over it real quick. In the past, I used to put it on a test, but I decided this semester I won't, and last semester I didn't either. So you get a gift. So what you do is use this formula, C1 times V1 times C2 times V2, and there are 2 steps. First, you have to calculate for what's your final volume, because you're usually given initial volume, initial concentration, and a final concentration, which is always less than the initial. And you're trying to find first the final volume. Well, really what you're trying to find out is how much do you add of solvent to the dilute the solution, and V add is V2 minus V1. Enough said, you can go back and look at this. All right, switch is on. Now, every once in a while you think about, is that a solution? And turns out it really isn't. There's something called colloidal dispersions. And colloidal dispersions are dispersion of small particles of one substance in another. They're really not solutions. We call them dispersions. And they're not really dissolved. Now, I will not ask in part two, we use terms like disperse phase instead of solute and dispersing media instead of solvent. But you should know, hint, you should know what are examples of colloidal dispersions. Milk. Milk is actually water with fat and protein dissolved in it. Latex paint is the latex in water, and your blood is not a solution. It's got different things dissolved in water, like proteins and carbohydrates and fats and oils. No, they're not dissolved. They're dispersed. Now, how can you tell? I don't have it here. How can you tell a colloidal dispersion? This is important. Take notes. Colloids or colloidal dispersions disperse light. What do I mean by that? All right, let's assume I dissolved sugar in this bottle of water. Here's one of my flashlights. By the way, Dr. White is a flashlight fanatic. I think I have about 15 or 20 of them. And notice the light goes right through. Now, if I had milk and a glass of milk, which I don't, but pretend there's milk in here, you wouldn't see this light. And if you don't believe me, try it at home. Now, do not try it with your blood, please. But here's another one you probably didn't think about. Take a jar of mayonnaise, hold it up, put the light like this, and nothing will come through. And that's how you tell if something's a colloidal dispersion or not. Will it disperse light or not? Why doesn't light go through? Because the little particles that are really not dissolved block the light and shoot it off. So remember, colloidal dispersions disperse light, light won't go through it. I'll say it again. Colloidal dispersions disperse light and light won't go through it. Now I have in this one boiling points, but let's go to chapter 13, part 2. Now in here, and I should have done a little more editing, and I apologize. First of all, let me make sure. Where it says exothermic change and endothermic change and change the state, I'll cover that next chapter better, so we're going to skip that right now. Now, part of this, the switch is off, but I'll tell you when it's on. I think most of you have seen water boil. You put a pot of water on a stove, you heat it up, all of a sudden you see these bubbles come up, and you look at that, and the water gets very hot, and you can cook food in there. Well, what is boiling? What is the boiling point of water? And let's talk about this because there are a couple things you should know for test 3. Now, a couple of terms that I'm not going to ask on a test. What is evaporation? That's the process in which molecules escape from the liquid phase to gas phase. So if you have something evaporating, it's a liquid, and the molecules in that liquid become a gas. If you ever put, and do not try this at home, if you ever take and put gasoline on a surface, come back a day or two, it's going to be all gone because it evaporated. Same thing with water and higher when it's hotter out. If you put some water on a sidewalk, come back a day or two later, it will be gone because it evaporated. Now, for evaporation happens at a quicker rate for hotter than cooler. And evaporation, when something happens where it evaporates, what's left behind gets cooler. Now, when you have something evaporate, it takes energy to convert the molecules from a liquid to a gas. Ooh, that was a good new one. Hey, warning, it's the first time I've ever done this, to a gas. It might be the last time too, but now I did it again. All right, now, time to, how should I say, to be politically correct. Let's talk about sweating. Now, men sweat, remember women perspire. How does that happen? Well, you got some moisture. Say you just worked out real hard, like with weights or running a couple miles, or you played tennis for an hour. And for Dr. White, he'd be dripping all over the place, sweating. Remember, women perspire. And what's happening? Why does that happen? And again, remember the last time I took biology was freshman year of high school, but this involves chemistry. You have liquid water on your skin and it evaporates because your body released it. And when it evaporates, it takes energy, and that energy cools you down, which is why when it's very humid, there's a lot of moisture in the air, it's hard for that water from your body to evaporate. That's why if Dr. White plays tennis, when it's in the humidity like 90% and it's like 85, you can put a bucket under me because I'm dripping so much. Usually I keep a big towel nearby. Headbands just don't do the trick. I haven't played tennis in a while. Unfortunately, my tennis buddy about a couple of years ago moved out of the area. But anyways, back to that.
Dr. White, did you send us email about about a chemical kit for like for money back?
Talk about what?
About a chemical kit, about a money back?
I mentioned that.
Did you send the email or not yet?
Not yet. I just
Oh,
mentioned it before. With my back, I've been having problems still. So
That's
I'm a little
okay.
behind.
Yeah.
Oh,
Okay.
it's not okay. Bad back. I can blame my back. Actually, I should blame me. Bad Dr. White. Everybody know what this means? Shame, shame on you when you're a little kid. Your parents ever do that? Never mind. But anyways, now, when you have water evaporating, the surface it evaporates from is cooled down. And if you ever seen by chemical plants or other places, they have what's known as cooling towers. And how does cooling towers work? Let's go real quick. Everybody see the cooling towers on the screen now? All right. What happens is you have fans on the top and you have water dripping down like over here. And the air comes in and evaporates the water. And there are pipes that are in there that have water going through it, and that cools it down. If you live in Arizona, and I'm not sure about Florida, instead of air conditioners like we have, they have what's called swamp coolers, which use the same thing. And these are cooling towers. Notice here you have the fans on top, pipes coming in, you have water being dripped down, air coming in, evaporating that, and that cools the water in there. Time for a quick Dr. White story. Many years ago, I was running a very important reaction for the first time at a plant in Morris, Illinois. I worked for the company Axo. And this reaction gave off a lot of heat. And that was part of the trick. How can we make it go with existing equipment that could only cool it down? Now, I knew the plant manager at that plant was not cheap, was trying to always save money. And they had 3 fans on the cooling towers, and he only ran 1. By the way, each fan was about 10-foot diameter blades and a huge motor. So by only running 1, he saved a lot of electricity over the month, which saved money and made him look good to the company. Well, anyways, I'm running this reaction. It was quite a dangerous reaction. And we're in the control room about 400 feet from us was a reactor that had 40,000 pounds of chemical, including 5,000 pounds of very explosive hydrogen. It was a hydrogenation. If you take organic chemistry, you'll learn what that means. And what happened is the temperature started going up. We had both a graph and a digital readout. Think of a swimming pool, and the temperature in less than a minute went from 120 to 100, 110 to 160 degrees C. That's pretty dangerous. And if it kept on going, that reactor would have blown up and Dr. White wouldn't be here. And a lot of other people would be dead. And I was at the control board and the operator, what do we do? And luckily I knew about it, and I immediately asked to the other side, other part of the control room, there was a worker there, how many fans do we have on? The cooling towers, 1. Turn the other 2 off right now. And another worker said, should I evacuate the plant? Because there was a thing you pull down, set off a steam whistle, real loud alarm, everybody should run away for your life. And he was about to pull it, and I said, turn on the fans. No. And the guy luckily did it. And then everybody got religion real quick. And about 30 seconds, 10, 15 seconds, you saw the temperature on the graph level down and come down to 130 where we wanted it. And that was the closest I've ever come to being dead in a chemical plant. But my knowledge of the cooling towers, by having more fans evaporating more air or water, made the water going through those cooling pipes in the reactor be cooler. Now, let's talk about, again, this definition you don't have to know, but what's vapor? That's gas molecules of a substance at temperature and pressure, which would normally be a liquid or a solid. When we talk about water vapor in the air, which we call a special name humidity, well, your boiling point, and I'll explain this in a second, of water is 100 degrees C, but if you're walking around in the summer and it's very humid, a lot of water vapor, it's not 100 degrees C, and that's why we call it water vapor. Now, there's something called equilibrium, and again, switches off. That's when 2 opposite processes take place. And another thing, since the vapor is a gas, you can measure the pressure. I'm sorry I'm going quickly, but I'll slow down. I'm going to go a little longer today, so hang in there. By the way, volatile substances like gasoline vaporize very quick and form a high vapor pressure. Now, let's talk about boiling. But first, warning, Dr. White artwork, warning, you're allowed to laugh, but don't fall off your chair. This is a hot plate. Or I could have had a Bunsen burner. Here I have a beaker. Actually, this is better artwork than normal. Of water. And after a while, you'll see these little bubbles come up. And they collapse. And what's in the bubble? Water vapor, water and a gas. And that goes like this. It's a gas that has a pressure. And some of it does come back, but you can measure it. And out here we have atmosphere. There should be a P there. Dr. White can't smell. And when the atmospheric pressure equals the vapor pressure, when that occurs, the temperature of the liquid we call the boiling point. This you should know. When the atmospheric pressure equals the vapor pressure, that temperature of the liquid is the boiling point. And at atmospheric pressure, the boiling point of water equals 100 degrees C at 760 torr, or 1 atmosphere. Now, something else you should know. If you go to Denver, the atmospheric pressure is much less than 760. This is switches on now. The higher you go on the planet, this you should know. The higher the altitude, the lower the atmospheric pressure. So in Denver, which is a mile-high city, the atmospheric pressure is much lower, and therefore the boiling point, this you should know, is lower than 100 degrees. I think it's 95, but don't quote me. And if you've ever been to Denver, and I have friends who used to live there, you'll see on things like rice or noodles, which you boil, you've got to boil them, if you did in Chicago, 8 minutes, you got to boil them a lot longer, because it's lower pressure. The lower atmospheric pressure means there's less energy you need to create this vapor pressure equal to atmospheric. Therefore, the boiling point is lower. Again, you should know this. The higher you get in the atmosphere or at altitude on our planet, the lower the atmospheric pressure. Because of that, the lower boiling point. If you go to the top of the Himalayas, which Dr. White won't, but the boiling point of water is very low compared to here in Northern Illinois, and you should know that. Now, the opposite of that is, how many of you have ever heard of pressure cookers? And pressure cooker, you have something sealed in there. You always have some water in there. And because it's under high pressure, the boiling point of water in the pressure cooker is much higher, because the pressure to have equal the pressure, vapor pressure in that container takes more energy. It's at a higher temperature. That's why you cook food quicker. Then pressure cooker temperature is higher. When you go up higher altitude, the pressure is lower, atmosphere, therefore the boiling point. You should know that. And wink, hint, hint, wink, wink, say no more. That's from Monty Python and the Flying Circus. Now, the last thing I want to talk about from these chapters is something called colligative properties of solutions. And it's important in our daily life. And certain physical properties depend on concentration of a solute in a given solvent, and not always on their chemical identities. And when you have this, important thing is you have boiling point elevation and freezing point depression. Coming up soon, unfortunately, even though I like winter, but it's going to get cold outside. And what do you see on your sidewalks on the street? Ice. And what does our townships do? They put either sodium chloride on the street if it's not too cold, but if it's real cold, they put calcium chloride. Now, why? Because with the ice, and when you push a little pressure down, the calcium chloride interacts with the water to form what's called a colligative effect of the solution, and that a colligative effect, the calcium chloride and sodium chloride lower the freezing point of water, and therefore it becomes a liquid and isn't as dangerous. Now, the other thing that you're not familiar with, but I'll teach you, in your car, there's a mixture, not just water in your radiator, but water and a chemical called ethylene glycol. And again, you get the colligative effect of that mixture. And what happens is the melting point or freezing point of the liquid is much lower than water. So if it's 20 below outside, not the wind chill, the actual temperature, your radiator won't freeze up solid and ruin your car. And the summer, when it gets very hot outside, your radiator gets higher than 100 degrees C. The water in your radiator doesn't form steam and damage your car because of the colligative effect. It has a higher boiling point. So when you mix things together, it will affect the melting point or freezing point and the boiling point, and that's the colligative effect. One is when we put salt or calcium chloride on the street ice, it melts it because of the colligative effect. You should know that. Also, excuse me, I need some water. This is thirsty work. In your car radiator, you have a solution of ethylene glycol and water, not just pure water. Back in the 30s and 40s, they used to use water, and people would have to take and melt their radiator. But anyways, we learned better through chemistry. And that's something you should know. Now, I didn't take out osmosis. I'm not going to talk about it. It won't be on the test. The only other thing from the other chapter, which I'll mention right now, I might have talked about this, but let me really quick do this. We look at water because of the difference in electronegativities of hydrogen and oxygen. This means delta, lowercase, minus charge, plus charge, plus charge. There's a slight minus charge on oxygen, slight positive charge, opposites attract. So there's this very slight attraction between the oxygen and hydrogen water. And this is called, even though it's not a real chemical bond, it's called the hydrogen bond. And this is, even though a very slight effect, is a very critical effect. Because of this, the boiling point of water is much higher than comparable molecular weight compounds, and that's because of hydrogen bonding. And molecules that can hydrogen bond and I apologize for going over, but I want to finish everything today, are molecules that have either nitrogen, oxygen, or fluorine with a hydrogen atom. So that means ammonia can hydrogen bond, hydrogen fluoride, water, and alcohols. If you take organic chemistry with Dr. White, I don't teach it at COD anymore, I teach it at ECC, also can hydrogen bond, and also an example of molecules with a hydrogen, oxygen, sugar can hydrogen bond, which is why it's so soluble in water. And with that, I apologize for going a couple minutes later, but no lab, so I'm going to let you out early anyways instead of going till 12:30, so you can all go, yay, Dr. White. But with that, don't forget, next Tuesday, I will be going through the solutions problem set. Do the problems. Next Tuesday, I will be doing my world famous review for the next test, test number 3. Please stop by or watch the video. And a week from today, we'll have the test number 3. After the actual lecture we'll have on Thursday, I'll send out a PDF file just like I did in test 1 and 2. You'll have until Friday morning, 10 a.m. to get it back to me, upload as a single PDF file, and that's about it. Everybody, have a great rest of the week and weekend. Enjoy the nicer weather. And with that, I'm going to say goodbye. Stay gesund, be healthy. I'll see you on Tuesday. If you need any help, my office hour is on next Monday. Stop by. With that, goodbye. As Granny would say, goodbye.